Okay, on to lesson 2 of forces at an angle. So let's take a look at the definition of the word friction first. So it's the force that exists when surfaces come into contact. So whenever surfaces come into contact, there's always going to be friction. And again, we're looking at Newtonian mechanics and not at the quantum level, okay? Quantum level, things don't actually touch. But with the big macroscopic Newtonian physics, they do touch. And when things touch, there's always going to be friction, okay? So the one more thing about friction that we should note here is that friction basically opposes the motion or potential motion of the object. So if you're going right, friction is actually going left, right? Friction is needed to stop an object. Okay? So if you are, for example, sliding, if I take a book and I just let it slide on a table, you see this? I'm going to just let it slide. I'm going to give it some force, initial velocity, and eventually it stops. Why? Because it came in contact with the table, and every time things come in contact, there's going to be friction, right? What if there is zero friction? What do you think would happen? If I take that book and I slide it, say, at 5 meters per second, what's going to happen to the speed of that book? It will be constant, right? Constant velocity, meaning it's going to keep going that straight line with the same speed forever and ever, right? Yeah, in the same direction. But because there's friction, it is needed to stop the moving object, but it is also needed to move a stationary object. Did you know that? So let's say you have a car and your car is stuck on snow. How are you going to move? How come you can't move that car? Because it's slippery, because there's no friction, right? So let's say I'm standing in the middle of a very icy, frictionless, frozen lake. If I'm in the middle of a frozen lake and I'm trying to walk, do you think I can even walk? I'm an object at rest, a stationary object. So in order for me to actually walk, right? You see, I'm walking on this floor. I actually have to use the friction between my feet and the floor so that I can move. If there's no friction between my shoes and the floor, I won't be able to move. Okay, so friction is not always bad. Friction is needed to move a stationary object, but it's also needed to stop a moving object. So that's what friction does to an object. So what is static friction? The word static means what? Means stationary, right? Not moving, at rest. So static friction, so friction, all forces, a symbol of a force is F, right? So F stands for force. Any capital letter F, it means force, right? So Fs is static. Actually, it's a frictional coefficient. So Fs is a static friction. Ff, by the way, is frictional force. So static friction and kinetic friction would be a different one, and we'll get there. So static friction is the friction, the frictional force that I'm gonna just put quote on that. Basically, the frictional force that holds the object to the surface. It's kind of like you're stuck there. It's like Velcro. So if you look at something like this, they actually look like, so these are surfaces in contact. If you look at it under the microscope, your hand, for example, if you look at your hand, oh, I wish I had my phone on me. I just have a picture of my daughter took a she likes to work with microscope. She's 7 years old. She has a microscope at home and she looks at different kinds of stuff. And she put her finger under the microscope one day and she likes to take a picture of it, right? So she saw that there are so much, like it's very rough. Your fingers are so rough, right? So there's a lot of friction on that. So if I were to take this water bottle here, and I'm just gonna use my fingers without grabbing it. You see how you can do this? That's because of your hands actually coming into contact with the water bottle and forming kind of like a Velcro like that. It's like a Velcro that holds the two surfaces together. So it's clinging to each other. So that is the static friction. So for example, you have an object at rest on a table. So that will have a static coefficient. It's called the coefficient. We'll get into that in a second. I'm going to write that here. So the static coefficient is called mu with the subscript s. Okay? Does that sound familiar? Okay? So mu s is basically the amount of the ability of the two surfaces to stay together. That is called the static friction, to keep it at rest. Okay? So static coefficient is something that is holding the two objects that are in contact together. So that means if you need to move the two objects together, like for example, you put your two hands together and you got fingerprints, that actually adds friction so you can grab objects with that. Your fingerprints are not just for identification. They're unique to everyone, but that adds friction. So that's the purpose of that. And if you rub your hands together, you know why your hands warm up? It heats up. So go ahead and just go like this and rub your hands together. It warms up, right? When you're outside waiting for the bus, waiting for your friend, and you do this when you're cold, your hands become warm that way. Why is that? Because every time things come into contact, right, they will have friction. And when you rub it together, that kinetic energy will add to the heat. It will convert into heat. So heat is always the result of objects rubbing together. So friction is bad that way because it breaks machines.
We sometimes snow is 0 of degree.
Yeah.
And then when the vehicle step on it, the snow melts. So this is.
Sometimes snow can help actually with the friction. So
It does get melted though, like because of the tire.
the tires spinning on snow, right? So because there's no the static coefficient is very small because there's very little friction, and that's why you can't, if you stop and then you have a very slippery road, it's hard to get going because friction is needed to get going. Yeah, you need friction to move. You need friction to stop. It's interesting, right? Okay, so kinetic force. This is actually kinetic, so kinetic friction, not kinetic force, so we'll change that. So kinetic friction, we're gonna write down mu k here. So mu k, so you had the mu s for the static. This is called mu s. This is the kinetic coefficient of friction. And basically this is for dynamic system. This is for moving objects. So when objects are moving and they are still touching, so surfaces are still in contact, then you're dealing with the kinetic friction. Okay, so there's still friction, but it's now moving. Okay, so the mu k is the coefficient. Now when you say coefficient, it's just a number. It's just a number. It's the coefficient that keeps the moving object in contact with the surface. So let's say you have an object that's already moving with some V. So you want to stop that. So to stop this object, you need to overcome that mu k. Okay, so that is the coefficient. So it's kind of like a number. It's just a number. There's no unit, and you'll know why. It's just a number that you need to kind of overcome to stop this moving object. Whereas the static coefficient is a number that you need to overcome to move a stationary object. That makes sense. Okay, so I'm going to write a little bit more about friction here on the side. So frictional force, right? So let's just put an object's free body diagram here. So free body diagram. So you got your FG. What else? Why is that object sitting on the table? Because the table is pushing back up. That's called the normal force, Fn. So if it is in a state of equilibrium, now equilibrium, remember, it could be a static equilibrium, object could be at rest, or it could be a dynamic equilibrium. As long as the acceleration is 0, we are in a state of equilibrium. When the acceleration of 0, the net force is, which is equal to ma, is got to be 0 as well. Because whatever mass you have, if your acceleration is 0, it's still 0. 0 times a billion is still 0, right? Okay, so I'm gonna now take a look at this free body diagram. So to calculate the frictional force of something, of anything, you have to have your coefficient, whatever that is, multiplied by the surfaces in contact. Remember, it has to have contact, right? So when things are touching, there's always gonna be friction involved. And that is the F of n, because F of n is the surfaces in contact. So if I'm leaning on this wall, for example, I'm leaning on the wall, okay? I'm pushing on the wall. You know that the wall is pushing me back, right? So this is a basic physics that you learn in 30S. If I lean on the wall is leaning on me, okay? You know that. Okay, so it's kind of like you have this table. That's basically you sitting on that chair. Your FG pulling down, right? The surface is not allowing you to sink to the core of the planet because the Earth is trying to pull you down. Okay, that's your FG. The table or the chair is actually pushing up on your body. So these two are in a state of equilibrium. Okay. It's not action and reaction, by the way. This example here is not action and reaction. Most people will think so, but we're gonna get into that in more details. Okay, so mu k, in this case, if you are moving, or mu s, or mu if you're stationary, it doesn't matter. So I want to now isolate the mu. If I were to isolate the mu from that equation, this one here, what is gonna be the formula for mu? What is it? You divide this by Fn, divide this by Fn, so this will be Ff over Fn. And what is the unit for forces? Newtons, right? So, and that is a force. All forces, the unit is Newton, named after Sir Isaac Newton, right? So a Newton divided by Newton is what? N over N. So, as you can see, the mu is unitless. It has no unit. It's just a description of the ability of the touching objects to either stay moving or stay at rest. It's just a number to describe. Okay? So as the mu increases, can I just use the arrow? Upgoing increases. As the mu increases, the basically the frictional force will increase. So that means the mu, by the way, mu is just the measure of the textures, the texture, the roughness. The rougher the objects in contact, the higher the mu. Does that make sense? So if you're standing on ice, for example, very smooth ice, frozen lake, would you have a greater mu on that than if you were standing on this cement floor? Which one would have a greater mu? The floor, because the floor is rougher. It has more friction because it has more mu. Okay, so it has more friction. But the answer to that is, if you have more mu, you'll have more friction. Because look, mu is proportional to the frictional force. Okay? Okay, so you know the expression, oh, butterfingers, right? You know when you're dropping stuff because it's slippery, right? Butterfingers, the origin of that is if you're cooking and your hands were greasy, or if you just put lotion on your hands, what you're actually doing is you're reducing the mu of your hands. So when I put lotion on my hands, I've just reduced the mu on my hands, which means that whatever I touch I could drop because I've reduced the frictional force. Okay? When you do that, when you rub it, the harder you rub, the more friction you actually will get. So why is that? Because you're actually pressing harder too. The harder you press, the more that force is going to actually be there, right? And the heavier you are because look, can you guys tell me are these two are going to be equal because it's in a state of equilibrium. So this is something that we were just looking at yesterday, right? The force up and the force down in this example, there you go, N equals Fg, right? Net force is 0. So if I were to ask you, well, how do you calculate your Fg? Mg, right? So if you know your Mg, which is your Fg, that's how you calculate the Fn. There is no formula to calculate the normal force. Normal force is basically how hard a surface is pushing on whatever is sitting on it. So if you're sitting and the earth is pulling you down, that's your mg. The chair is pushing up on you with the same amount of force. Okay? So to calculate frictional force, you're gonna go, let's say Matusala, your mass is 70 kilograms times 9.8. That's your Fg. That's also your Fn. That means that chair is pushing up on you, that is equal to your weight. Can you tell me what would happen? What would happen if your Fg is great? Can this happen, by the way? Can Fg be greater than the maximum Fn that an object can push back? Yes, it can happen. You know what? If I'm sitting on a kid's chair, for example, that is made of a very thin plastic and it's designed to hold a child's weight, for example, and then I sit on this chair and then I broke it. What does that mean? It is not designed for my Fg. That means there's a maximum amount of normal force that chair is designed for. Okay? But if something is not breaking, if I sit on a chair or a table and the structure is holding, that means the Fg is equal to Fn. Okay? If the Fg is greater to the maximum Fn that structure can hold, then what would happen? This thing will break. It breaks, then the chair will break because my Fg is too big. Okay? Same thing with the tension force. I'm just gonna go back and review tension because we were doing a lot of tension yesterday. So let's say there's a string, a rope hanging, and then I decided I'm going to hold on to this. There's me now. I'm gonna hold on to this and just hold on to this rope and swing. Okay? So obviously you'll have your Fg and you'll have your Ft going this way. If you look at these lights that we have and it's got a cable that's holding it up that way, holding it up, and then Fg pointing down, is that light above your head breaking? No, it's not. Look at it. It's still up and intact and it's not moving up and down. It's not moving side to side. Can you then say that is in a state of static equilibrium? You bet. There's no motion whatsoever. What is the net force on that light? Zero. Because the Ft up is equal to the Fg down. What if my Fg, let's say my weight is 600 newtons and this rope can only hold a maximum of 500 newtons. What's gonna happen? I'll break that rope. It's gonna break. But if it's holding and it's not breaking, then what that means is that the Ft, if it doesn't break, and my Fg is 600, that means the Ft must also be 600 newtons. That is a good state of equilibrium. No one's getting hurt because it's designed to at least hold 600 newtons of weight, or probably more, right? But it's never gonna be, let's say I'm holding on to that string and it's 600 newtons of weight, it cannot exceed that. So the rope can only hold a maximum of whatever is hanging on to it. Okay, but it can be less if it's designed that way.
When the FG is 600 newton, about for those 3 FG?
Very good question. Let's say the light is 600 newtons. You're gonna have to divide the 600 by 3. You're right. You're right. Exactly. So each one is gonna hold 200 newtons evenly. Unless we put that at a different angle, and then we'll have to calculate the FTY. Just like what we did with all these. Okay? Has anyone gone fishing before? Have you guys gone fishing? When you go fishing and you buy those fishing line, the line that you add to your fishing pole, okay? You have to buy the fishing line that is designed for the fish that you're intending to catch. So if you're gonna go fishing in the ocean where you're looking for fishing for a big tuna are huge, or swordfish, or a shark, you're gonna need to buy a fishing line that has, it will tell you maximum FT of 1000 newtons. If you're going to, and it costs more, if you're gonna go fishing at the Red River, for example, and you're gonna look for silver bass or pickerel, which is small, right? Then you can go to Canadian Tire and just buy the cheap one, or go to Dollarama, buy the cheap one, because the FT that it's designed for is maybe 20 newtons. Okay? So you have to adjust that because each structure has a maximum that it can hold. Strings have a maximum FT, and objects will have a maximum FN that it can support. Okay? All right. So now let's take a look at this example. Any questions so far with the concepts of friction? Okay, let's take a look at example 1 here. So again, the first thing is you need to figure out what the question is, right? The wordings, what does that mean? Okay, so let's read this. It looks like a concept question because it says indicate which 2 answers are wrong and explain why they are wrong. Actually, you know what? Before, should we do this right now? Yeah, let's take a look at example 1. This is a concept. So you have a 15 Newton applied force at 30 degrees to the horizontal. And so you take a look at, here is the object on the floor, and 30 degrees to the horizontal. So let's make a sketch first. So here we are, and this is 30 degrees that way. So you know what? The first thing I do is I read the question and I make a picture. That's a good technique. Don't overthink it. Just make a picture right away. What is this line right here? What kind of force is that? Applied force. So let's label it FA. Okay, what else is happening? Okay, you know what? Let's complete the free body for this one before we move on. Can you guys complete the free body diagram for this one? It's sitting on the ground, so what forces are acting? Okay, so let's take a look back here. Did you put your FG? Okay, your FG down. And if the floor is not breaking, there's Fn up, right? These two are equal in size, in magnitude. And then it says here, it says that it accelerates a box across the horizontal. So that means then the net force, this is net force. Okay, so I'm just gonna write down here, net force is how it's moving and where it's moving. It's directed to the motion of the object. So what does this look like? So imagine you're dragging something. It could be with your arm or with a string. Okay, 30 degrees from the floor. This is you. This is your actual pulling force. So this is you pulling. But if the box does not leave the floor and move this way, the force is actually just along the x-axis. So the motion is in the horizontal only because you're not lifting it. So if the motion stays in the x-axis, that is going to be your net force. Okay? Do you think there's going to be friction in this one? It didn't say frictionless, so there will be friction, right? So where would the friction be pointing towards? Opposite of the net force. Not FA, net force. So this is going to go this way, and we'll label that FF. So here's what's happening. It's not to scale. I'm not saying that because this is longer that this is a greater one. I'm just doing the free body diagram for now. So let's take a look at the rest of the question. So there's Glenn, there's Olive and Warren, and they're discussing the problem. So Glenn suggests, and I'm going to write down here, this is what Glenn said. Glenn said that the normal force is 50 newtons, okay? And then there's Olive. Olive said that the Fn is 75 newton. And then there's Warren. Warren said that the normal force is 100 newtons. Okay. While all three answers may seem reasonable, only one is correct. Indicate which two answers are wrong and explain why they are wrong. So we're going to do this by elimination. What do we know here? What's given? So you see the 50N there? What is that? That's the applied force, right? So this is the 50 newtons. That's the applied force. Okay. So we're looking at the normal force, and we only are given the applied force. What should we actually now try to figure out? So we know that this is being pulled that way or pushed at 50 newtons at an angle of 30 degrees. What can you solve from those two things that we know? Huh? X and Y, that's right. So can we find this will be the FA of X. We can solve that. Can you guys do that? And then we can also solve for the FA of Y and see if that can help us solve that, the question. How would you do that? Go ahead. So for this, it will be sine, yeah? So it will be 50 sine of 30. Okay, give me the number. And then FA of X is 50 cos of 30. Okay, let's get the numbers there. So, what's the FAY? 25? And what is the FAX? 43. Okay, so there's what we know. That's all we know. That's all we're given. Is there a way? Can you guys write the formula for this one? Write the formula. Well, in the y-axis, we know that Fn equals Fg. Why would I say that? How do you know that? Is that actually all it? No, it's not all it, right? Let's take a look again. Let's double check. That's what we've been doing before, but this time it's actually being pulled at an angle. When you pull something at an angle, this is not true anymore. It's no longer true. And the reason for that is when you're pulling something at an angle, you're kind of lifting it. You see that FAY is the lifting force. You're lifting it a little bit, right? So what are the forces that are going up? What are the forces going up? Well, there's the Fn. What else? FAY, that invisible force. Those are both going up. So if I were to ask you to write the net force equation on the y, can you tell me what that would be? What would you do with those two? Minus or add? If they're in the same team, they're both going in the same direction, they're helping each other. So you'll add them, right? So then we'll go Fn plus Fay. But then there's a force going down. So there's this force going down. What do you do with that? Minus Fg. And this is equal to 0. How do you know that? It's not moving up and down. Yes, you lifted it a little bit with your Fay, but it's not actually leaving the floor. Does that make sense? Okay, let's finish this off. So if that is the case, I'm going to here now, expanding on that. So how can you solve for the Fn? Can you solve for Fn from that, from what we know? So Fn then is equal to, what do you have? Move the Fg over to the other side. That will become positive, won't it? Oh, Fg. Yes? And then I'm going to move the Fay to the other side. What would happen to the positive when you move it across the equal sign? Become negative. So this will become Fg minus Fay. That is how you'll calculate your f of n. Right? Okay? So let's take a look now. Let's take a look here. What would be the most probable answer? Let's do it by elimination. Remember the Fay? What was our Fay? Remember Fay is 25 newtons, right? But we have no idea what the Fg is. Okay? So let's do it by elimination. Can Warren, let's go this way. Can Warren be right? It says 100 newtons. Can Fn be 100 newtons?
No.
Why not?
Because we have the 25 minus probably would be 35.
You're subtracting the 25. But how? Okay, how? Let's actually, Fa is 50. So we solve this to be 25, right? How about in the x component? What are the, we got 43 going this way, right? So we're looking for the Fn, so we don't care about the f of x actually. Can you actually have an Fn of 100 newtons?
Depending on the Fg.
Yeah, we don't know the Fg, right?
Because you don't know the mass.
Yeah, we don't know the mass, so we can't find the Fg. So we're trying to do this by reasoning. Which one, which two answers do you think are obviously wrong?
50 and 100.
Which one of these three?
Glenn and Warren.
Glenn and Warren, you think? Okay, let's plug it in. If the Fn is 50, let's take a look at, if I were to solve for Fg, then Fg will be Fn plus Fay. That would be, what would the Fg be if I were to solve for it, right? So if Fn is 50, if Fn is 50 plus Fay, so 75, is it possible to actually have that? What do you think? This makes it very hard actually because the mass is unknown, right? Can I leave this to you guys to think about tonight? Without the mass, I want you to just, this is going to be a reasoning question and then I'll elaborate on this tomorrow. And I think it's the go.
That's not a formula.
There's no, that's the only formula that we have here. I want you to think about this. This is more of a brain exercise for you guys. So, by reasoning, no calculation. Okay? So then we'll pick this up first thing tomorrow.